Look up at the night sky for a moment. Those tiny points of light may seem close, almost like decorations scattered across a dark ceiling. But in reality, each one could be a star hundreds or thousands of trillions of kilometers away. And beyond them lie entire galaxies, billions of stars drifting through an ocean of space. The observable universe spans tens of billions of light years. That's a distance so vast that even light, the fastest thing in existence, needs billions of years to cross it. Inside this enormous cosmic arena exist hundreds of billions of galaxies. Each galaxy contains billions of stars, planets, and unknown worlds. But here's the real mystery. If the universe began in a tiny, dense state after the Big Bang Theory, why did it grow to such unimaginable proportions? What force stretched space itself until the cosmos became so staggeringly large? In this journey, we'll travel from the smallest quantum particles to the largest structures ever discovered. We'll explore expanding space, cosmic inflation, galaxies, and the enormous web that binds the universe together. And along the way, we'll uncover the surprising reason why the universe became so vast. Because the answer to this question may change how you see the cosmos and your place inside it. The observable universe stretches across distances so vast that ordinary imagination struggles to grasp them. Billions of galaxies drift through space like glowing islands scattered across a cosmic ocean. Light from some of these galaxies has traveled for billions of years before reaching our telescopes. And yet, even that enormous distance may represent only a fraction of the true universe. When astronomers look into the night sky, they are not just seeing distant objects. They are looking back in time, watching ancient light that began its journey long before Earth even existed. Each tiny point of light may represent billions of stars bound together in swirling galaxies. The deeper scientists observe, the more immense the universe appears to become. But this raises an intriguing question that echoes through modern cosmology. Why is the universe so incredibly large in the first place? Why didn't space remain small, dense, and compact after the universe first formed? Instead, the cosmos expanded into something staggeringly vast. Imagine blowing up a balloon with tiny dots drawn across its surface. As the balloon expands, the dots move farther apart from one another. In a similar way, the fabric of space itself seems to have stretched over time. Galaxies drift apart not because they are flying through space, but because space itself grows. Still, the mystery runs deeper than simple expansion. If the universe began in an extremely small state, something must have driven it to grow to such colossal proportions. Something transformed a tiny beginning into a cosmos spanning billions of light years. To understand that mystery, scientists first had to discover just how vast the universe really is. For most of human history, the universe appeared small and simple. The night sky seemed like a dome filled with stars surrounding our planet. But as telescopes grew more powerful, that comforting illusion began to dissolve. The cosmos suddenly revealed itself as something far larger than anyone had imagined. In the early 20th century, astronomers realized that many faint smudges in the sky were not nearby clouds of stars. They were entire galaxies, vast systems containing billions of suns. Each galaxy drifted unimaginably far away from the others, separated by immense cosmic distances. The universe was no longer a single island of stars, but a vast archipelago scattered through space. Then came an even more astonishing discovery. When scientists measured the light from distant galaxies, they noticed something strange. The light was stretched toward the red end of the spectrum, like the deepening tone of a siren moving away. This phenomenon revealed that galaxies were not standing still. They were moving away from us. Even more surprising, the farther a galaxy is, the faster it appears to recede. This pattern suggested something extraordinary about the universe itself. It wasn't simply filled with moving galaxies. The entire fabric of space seemed to be expanding in every direction. Astronomers began mapping galaxies across enormous cosmic distances. They discovered clusters of galaxies, superclusters, and vast structures spanning hundreds of millions of light years. The more deeply telescopes peer into space, the more immense the cosmic landscape becomes. And yet this observation leads to another mystery. How could such enormous structures emerge from the tiniest beginnings? To understand the enormous scale of the universe, scientists sometimes do something surprising. Instead of looking outward toward galaxies, they look inward toward the smallest pieces of reality. Because, strangely enough, the story of the universe's vast size may begin at the tiniest scales imaginable. at a level so small that ordinary intuition completely breaks down. Everything around us, planets, stars, even galaxies, is built from atoms. Atoms themselves are made of smaller particles like electrons, protons, and neutrons. And those particles are governed by the strange rules of quantum physics, a world where uncertainty, fluctuations, and tiny bursts of energy constantly appear and vanish. Imagine the surface of a calm lake on a quiet morning. Even when the water looks perfectly still, tiny ripples are always forming and fading. In the same way, the quantum fabric of space is never truly empty. Microscopic fluctuations constantly ripple through it, like invisible waves in reality. In the earliest moments of the universe, these tiny quantum ripples may have played a crucial role. Small variations in energy were stretched as space rapidly expanded. Those microscopic differences eventually became the seeds of galaxies and cosmic structures. In other words, the largest patterns in the universe may have started as the smallest disturbances imaginable. It's a breathtaking thought. The vast cosmic web may trace its origins to subatomic fluctuations. From the tiniest scales of physics emerged the framework of galaxies and clusters. The universe grew from quantum whispers into a cosmic landscape billions of light years wide. But before reaching such enormous scales, that growth passes through something closer to home, the scale of planets. Before leaping to galaxies and cosmic webs, it helps to pause at a scale closer to human experience. Even within our own solar system, distances quickly become enormous. Earth, for instance, orbits the Sun at an average distance of about 150 million kilometers, and that's just the first step into the vastness of space. Imagine shrinking the Sun down to the size of a large beach ball. At that scale, Earth would be about the size of a small marble, but the marble wouldn't sit close to the ball. It would be more than 15 meters away. Most of that space between them would be completely empty. Travel farther outward and the emptiness grows even more dramatic. Jupiter, the giant of our solar system, would sit roughly 5 times farther from the Sun than Earth. Neptune, the most distant major planet, would orbit about 30 times farther away. Planetary systems are mostly empty space with a few scattered islands of matter. Even light, the fastest thing in the universe, needs time to cross these distances. Sunlight takes about 8 minutes to reach Earth. To reach Neptune, that same light must travel more than 4 hours. And yet, on the scale of the universe, even our entire solar system is barely noticeable. In fact, if our solar system were placed inside the Milky Way galaxy, it would look microscopic. Billions of other stars would surround it across distances so large that numbers become difficult to grasp. So scientists needed ways to measure these staggering distances. And that challenge led to one of astronomy's most ingenious tools: methods for measuring the size of the universe itself. Once astronomers realized how enormous space might be, they faced a daunting challenge. How do you measure distances so vast that traveling there would take millions or billions of years? Unlike measuring a road or a mountain, cosmic distances cannot be crossed with rulers or tape measures. Instead, scientists had to turn the universe itself into a measuring tool. One of the simplest methods begins surprisingly close to home. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. This tiny change in position is called parallax. It's similar to how a nearby object seems to move when you look at it from one eye and then the other. But parallax works only for relatively nearby stars. To measure distances far beyond our local stellar neighborhood, astronomers rely on objects known as standard candles. These are stars or cosmic explosions whose true brightness is known. By comparing how bright they appear from Earth, scientists can calculate how far away they must be. One of the most powerful examples comes from supernovae, colossal stellar explosions. For a brief moment, a single supernova can shine brighter than an entire galaxy. Because certain types explode with nearly identical brightness, they act like cosmic lighthouses. Their light allows astronomers to measure distances across billions of light years. Step by step, scientists built what's called the cosmic distance ladder. Each method measures farther than the one before it, extending humanity's reach deeper into space. With every rung climbed, the universe revealed itself to be far larger than expected, and those measurements uncovered something even more astonishing. The universe itself appears to be expanding. When astronomers realized that galaxies were moving away from one another, it forced a radical shift in how scientists viewed the universe. Space was not a static stage where cosmic objects simply drifted around. Instead, the stage itself seemed to be stretching. The universe wasn't just filled with motion, the fabric of space itself was expanding. To understand this, imagine dots drawn across the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. No single dot is the center of the expansion. The surface itself is stretching, carrying the dots along with it. The universe behaves in a remarkably similar way. Galaxies are not flying outward from a single explosion in empty space. Rather, the space between galaxies slowly expands over time. As that invisible fabric stretches, the distances between galaxies naturally grow. This behavior emerges from the equations of general relativity, developed by Albert Einstein. According to this theory, gravity is not just a force pulling objects together. It is the curvature and motion of space-time itself. Under certain conditions, space-time can expand, bend, and evolve. Over billions of years, this expansion has stretched the universe to extraordinary proportions. Galaxies drift farther apart, cosmic structures grow, and the observable universe continues to widen. Yet within this expanding sea of space, gravity can still gather matter into smaller islands of structure. And those islands eventually gave rise to stars, planets, and entire solar systems. Within the vast, expanding universe, gravity quietly begins its own kind of work. While galaxies drift apart across cosmic distances, small pockets of matter start pulling themselves together. Clouds of gas and dust slowly collapse under their own weight. From this gentle collapse, new stars are born. Our own solar system began inside one of these giant molecular clouds. Imagine an enormous fog of gas stretching across trillions of kilometers. At first it looks calm and diffuse, like mist floating through space. But deep inside, gravity slowly gathers the material inward. As the cloud contracts, it begins to spin, much like an ice skater pulling in their arms to spin faster. The collapsing material flattens into a swirling disk of gas and dust. At the center, pressure and temperature rise until nuclear fusion ignites. A new star is born, the young sun. Around this newborn star, leftover dust and gas continue circling in the disk. Tiny grains collide and stick together, forming larger and larger clumps. Over millions of years, these clumps grow into planetesimals and eventually full planets. Worlds like Earth slowly take shape within this cosmic construction zone. So even in a universe expanding across unimaginable distances, gravity still builds islands of order. Stars ignite, planets assemble, and solar systems emerge within the cosmic darkness. Our entire planetary home formed inside this delicate balance between expansion and collapse, and that balance would eventually create the environment where life on Earth could appear. In the grand map of the universe, Earth occupies an almost unimaginably tiny position. Our planet circles an ordinary star on the outskirts of a spiral galaxy. Nothing about this location appears especially unique when viewed on a cosmic scale. And yet, this small corner of the universe became the cradle of life. The vastness of the universe plays a subtle role in this story. Because space is so enormous, countless stars exist across billions of galaxies. Many of those stars likely host planets of their own. In fact, modern astronomy suggests that planetary systems may be common throughout the cosmos. Imagine walking along an enormous beach covered with grains of sand. Now imagine that each grain represents a star somewhere in the universe. Among those countless grains, many may have their own tiny worlds orbiting nearby. Some of those worlds could have oceans, atmospheres, and perhaps even life. From Earth's perspective, however, the universe still feels distant and mysterious. Even the nearest star beyond the Sun, Proxima Centauri, lies more than 4 light-years away. With current technology, traveling there would take tens of thousands of years. The enormous scale of space keeps most of the universe far beyond our physical reach. Yet that same vastness also invites curiosity. Humanity builds telescopes, launches probes, and sends instruments into space to explore. From our small planet, we continue mapping a universe that stretches far beyond imagination. And as astronomers look outward, they begin to see even larger patterns emerging across the cosmos. When astronomers zoom out far beyond individual stars and planets, an entirely new level of structure appears. Galaxies themselves become the building blocks of the universe. Each one is a vast rotating system containing billions or even trillions of stars. And scattered across the cosmos, these galaxies form enormous communities. Our own home galaxy, the Milky Way, contains more than 100 billion stars. If someone could travel across it at the speed of light, the journey would take about 100,000 years. That single galaxy alone is already almost unimaginably large, yet the universe contains hundreds of billions of galaxies like it. Galaxies rarely exist in isolation. Gravity gently pulls them into groups and clusters that drift together through space. Some clusters contain hundreds or even thousands of galaxies bound by their shared gravity. These clusters themselves stretch across millions of light years. Even larger patterns appear when scientists map the universe at the greatest scales. Galaxies form long filaments and walls of matter that weave through space. Between these filaments lie enormous cosmic voids, vast regions where almost nothing exists. Together, these structures form what scientists call the cosmic web. Seen from afar, the universe begins to resemble a gigantic network. Threads of galaxies stretch across unimaginable distances, connecting clusters like nodes in a cosmic web. These structures span hundreds of millions of light years, and their origins may trace back to the earliest moments after the universe itself was born. To understand why the universe became so enormous, scientists travel back to the very beginning of cosmic history. Everything that exists today, galaxies, stars, planets, and even space itself, traces back to a single origin. This moment is known as the Big Bang Theory. Nearly 13.8 billion years ago, the observable universe began in an extremely hot, dense state. At that time, the entire cosmos was compressed into a region far smaller than a galaxy. Temperatures were so intense that atoms could not even exist yet. Energy and fundamental particles filled the young universe like a blinding cosmic fireball. But something extraordinary happened almost immediately after this beginning. Within a tiny fraction of a second, space itself expanded at an astonishing speed. This dramatic growth is called cosmic inflation. During inflation, the universe may have grown from subatomic scales to astronomical sizes almost instantly. It was like stretching a tiny ripple on water into a wave spanning an entire ocean. This rapid expansion smoothed out the young universe and spread matter across enormous distances. Tiny quantum fluctuations were stretched into large variations in density. Over millions and billions of years, gravity amplified those variations. Eventually, they became galaxies, clusters, and the vast structures we observe today. In other words, the immense scale of the universe may be the result of its explosive early growth. A brief but powerful expansion transformed a microscopic beginning into a cosmic landscape. The galaxies we see today are part of that ancient unfolding story. And understanding that story leads to one final question about our place within it. When people first look at the scale of the universe, the numbers alone can feel overwhelming. Billions of galaxies, each containing billions of stars, scattered across unimaginable distances. Light itself takes billions of years just to cross a portion of this cosmic landscape. The universe stretches far beyond anything human intuition evolved to understand. And yet, despite this immense scale, humanity has learned to measure it. From a small planet orbiting an ordinary star, scientists have mapped galaxies billions of light years away. Telescopes capture ancient light that began traveling long before our species existed. Through patience and curiosity, the universe slowly reveals its structure. It's a little like standing on a beach at night and listening to distant waves. At first, the ocean seems mysterious and endless. But slowly, patterns emerge. The rhythm of tides, the movement of currents. In the same way, the cosmos begins to make sense as we learn its hidden laws. Still, the scale of the universe carries a profound message. Our planet is tiny, our lives brief, and our civilization young compared to cosmic time. Yet within this vast universe, consciousness has appeared, capable of asking questions about existence itself. The cosmos has produced a species that can observe and reflect upon the universe. And perhaps that is one of the most remarkable facts of all. In a universe billions of light years wide, a small world developed minds capable of understanding cosmic history. Human curiosity stretches across space just as telescopes do. And with every new discovery, the universe becomes a little less distant.